Light. It's understood that when we talk about light in this class in physics, we're talking about visible light. And as with the discussion we had in class, we really don't see light like we see things. We see things because light hits them. Our eyes detect light of a certain frequency in the electromagnetic spectrum, which we'll see at the bottom of the page here. But light, quote-unquote visible light, that which we detect with our eyes, what is it? Well, it's a form of energy. It's electromagnetic energy. It's a transverse electromagnetic wave. It transfers, its energy itself, it's transferring from one location to another location without the transmission of a material object. In this case, there's no physical medium in which the waves are traveling. Light, or any electromagnetic wave for that matter, have a particle nature as well as a wave nature. The particle nature of light we call photons. We'll talk about that later in the year. Now light travels at, well, not quite, but almost 1,000,000 times faster than the speed of sound. As we know, the speed of sound in room temperature air is roughly 343 meters per second. But the speed of light in a vacuum is referred to as c. c is, rounded off to 3 sig figs, 3.00 times 10 to the 8th meters per second. That's the speed of light, or the speed of any electromagnetic wave in a vacuum. And it's understood to be the speed limit of the universe. We can have a deeper discussion about that later as well. But anyways, all electromagnetic radiation, radio waves, microwaves, gamma rays, and so on and so forth, travel at that speed. Now, this is an incredibly fast speed. At that speed, it takes about 0.02 or 2/100ths of a second for light, or any electromagnetic wave, to travel the distance from California to Chicago. It would take about 1 second for light to get from the moon to the earth, or from the earth to the moon. We actually have reflectors on the moon that we put up there when the astronauts landed there. And we ever so often, or scientific laboratories, shoot up light or radio waves towards the moon, reflect them off those reflectors back to the earth to measure the round trip time, and therefore also to determine, using V equals D over T, how far away the moon is. And we've determined that the moon is getting slightly, ever so slightly farther from the earth as time goes on. Once again, this is a fast speed. However, the sun is so far away, like about 93 million miles on average, that it takes just over 8 minutes for light to get from the sun to the earth. So it's fast, but it's not infinitely fast. Well, there's been attempts to measure the speed of light over the years, but one of the most famous recent or accurate measurements of the speed of light was by physicist Albert Michelson. He was the first American physicist to win a Nobel Prize in physics in 1907 for his design of optical instruments, one such as this that was set up to measure the speed of light. And it was quite ingenious and simplistic in its nature, because basically the math that was involved is essentially V equals D over T. What he had, this is an overhead view of the setup, is he had an octagonal mirror on a mountain or a tall hill, Mount Wilson. I think this is in California. And he had another mirror on another mountain quite a ways away, San Antonio, well, 22.5 miles. We can convert to metric units if we want. We're not going to do that right now. But the M's here stand for mirrors, mirror 1 and mirror 2. All right, so he had a source of light up here at the top, shining source of light. And keep in mind, this is 1907. There's not real modern transportation methods, so to get from one of these locations to the other 22 miles away, you're basically using a horse or a railroad or walking or something of that nature. So this is quite a ways away, and to get this all lined up was quite a trick back in that day. It'd be quite a trick nowadays. But you have an 8-sided mirror, you shine some light on the first mirror, and it bounces off, following the law of reflection, which we'll learn about later on. And that light basically hits this mirror. Now he has a curved mirror here, and it shows a couple of reflections. But the bottom line is the light comes back and hits another angled mirror on this octagonal mirror, and then bounces into a viewer. They call it a telescope in this case, but a viewer that he looks in and sees the light coming into that telescope. Now, if nothing is spinning here or moving, they can get this lined up. Once again, it probably took him quite a while to get it lined up. He gets it lined up, but then what he did is he started spinning this octagonal mirror. Doesn't really matter which way, but in this case, let's say clockwise. And what happens is, as you spin this, everything goes out of alignment, so the light doesn't follow that blue. Well, it goes in straight lines, but doesn't end up going into the telescope because the alignment goes off as the mirror spins. But the bottom line is this: what you can do, is you can spin this so fast, because you had some good motors that could spin the mirror really fast. And what happens is, if you spin it so fast that in the amount of time it takes for light to travel the basically 45-mile round trip, 22 plus 22, 22 and a half, gives you 45 miles round trip down to that far mirror, back to the octagonal mirror. If you can spin it fast enough such that mirror number 1 spins towards and ends up in location number 2, and the mirror from location number 2 ends up in location number 3 in that amount of time. In other words, the octagonal mirror has spun 1/8 of a revolution. Essentially, if you know how fast the mirror is spinning, and you know how long it takes to make 1/8 of a revolution, if you can get it spinning fast enough such that the mirror becomes aligned up again, like in this particular exact position again, just all the numbers have shifted by 1, and it lines up, the light goes back into the telescope as the light comes back in the amount of time it takes to go and make the round trip of 45 miles. So basically what you know is the time. You know the time because you know how fast your mirror is spinning, you know how much time it takes to spin 1/8 of a spin, and you know how far away it is. It's just simple division there. The distance divided by time gives you the speed of light. And I believe he got within 1% of today's accepted value. So it was quite remarkable in a time what he did to measure the speed of light. So the electromagnetic spectrum, and you've probably seen pictures like this before, but on the top here you have the most common types of electromagnetic radiation, the electromagnetic waves. They're all the same thing, just different sizes. The one thing we're going to be highlighting here is the visible part of the spectrum, somewhat kind of in the middle of this thing, but the visible spectrum is a small sliver of the overall spectrum. On the far left we have radio waves, which have the long wavelengths, but they have lower energy and lower frequency. So they have, on the left end here, long wavelengths, lower frequency, and lower energy. Because the energy is tied to the frequency. We'll talk more about that in the coming weeks. But bottom line here is get an idea that they have the spectrum, and it's just a transition of sizes and frequencies, with the frequencies going up to the right. So you go from radio to micro to infrared to visible light. We're going to focus on visible light. And at the bottom here, they show you how the visible light then is split up into our Roy G. Biv, which you've probably considered before from a previous class. That stands for the typical order of colors that we see, quote unquote, in a rainbow or the visible spectrum: red, orange, yellow, green, blue, indigo, violet. Where the red's on the left and the violet's on the right, going from long wavelength red, which is low energy, low frequency, up to the short wavelength violet on the right hand side, which is the high frequency, high energy. And then this chart here also kind of shows you some relative sizes of these wavelengths. On the left we have the radio waves, which have wavelengths approximating like football fields, and then microwaves, which are butterfly size wavelengths, and so on and so forth, up to the atomic nuclei level for gamma rays and their wavelengths. Just have a general understanding of this spectrum, and knowing that visible light, the type that we can detect with our eyes, is a small sliver of this overall spectrum. All these waves travel at the same speed, and the highest energy is on the right hand side. Now there are three basic ways that we're going to represent light, or any electromagnetic waves, but light in particular. And as we said in class, once again, we don't really see lights. It's an invisible phenomenon, so this is a little bit of a challenge, representing this invisible phenomenon that we can detect with our eyes, but really can't see it traveling through the air. The most complicated or involved way is this first way, the mutually perpendicular transverse electric and magnetic fields. That's a mouthful. But, and the formatting on my notes here are a little bit different than your notes. But down here on the left, or on your left-hand side, is a good diagram of that. They have these fields that, self-propagating electric and magnetic fields at right angles to each other. In this case, they're using blue for the electric field going in a vertical direction, but the electric field could be at any direction. It could be horizontal, it could be at 45 or 38 or 22.5 degrees, but the important thing here is that the magnetic field is always perpendicular to the electric field, and it travels through space at a speed of 3.0 times 10 to the 8th meters per second. Now, it's probably going to be more useful to us, not that diagram, because that one's too complicated to draw all the time. We want to have a better way of drawing or representing light. So one way to do this is with wavefronts. All right, so this candle diagram kind of has all three ideas in one diagram. The blue circles, or almost 3/4 of circles, are the wavefront representation of light coming out of a candle as the light goes in all directions. And once again, you have to kind of imply or infer the three-dimensionality of actual light coming out of a light bulb. Say, and we usually talk about a point source of light. As the light comes out in spheres, kind of like throwing a rock into a pond, that's the two-dimensional version of that, as you drew in the lab we just completed. But those are wave fronts. Those are kind of like what water waves look like. And you could have straight ones, like if you're at a beach, but here we have circular ones. The other idea is to draw, well, you have the red wavy line there, which once again kind of is like the transverse electric field without the magnetic field. We don't want to keep doing that one. That one's probably the least useful as far as actually problem solving as we go forward here. But it's another way, a good way of representing something that's transversing through the air, traveling through the air from point A to point B. But another way, probably the most commonly used method that we will use, is the ray diagrams, where we have light coming out from a source. Once again, light does not look like this, but this is the way you might have drawn it when you were younger. Like the sun giving off light, we have rays of light. So that would be the ray model. Kind of just shows you the way the light is traveling. And it turns out that rays are perpendicular to wave fronts if you draw them in one diagram. Usually we'll just pick one method or the other, like these red arrows as rays. And we could draw infinitely many of these. There's rays going in all directions, but we only have a limited amount of time. So we draw, I've got about 10 or 12 here, but the light coming out, spreading out as it travels outward from the source, perpendicular to the wave fronts. Polarized light. Light with a single direction of vibration, usually referred with reference to the direction of the electric field vibrations. Most, if not all, light sources give off unpolarized light. It's got random vibrations. In other words, when, say, a light bulb or a candle gives off light, the electric field might be vibrating vertically or horizontally or at 22 degrees or at 15.7 degrees or 182 degrees. And then the magnetic vibrations are always perpendicular to the electric vibrations. But that's unpolarized light. Some books will call that randomly polarized. I don't like that term. I'm just going to call it unpolarized light. So if you want a polarized light, however, and you probably have heard of this with sunglasses. I have a picture on the left, and these notes it's on the bottom here. Polarized filters. You can polarize light by two basic ways, and usually we use special filters to polarize light. We pass the light through a filter, which acts like, as you see here in this one diagram, it's kind of like a picket fence for the light. And I'll do some demonstrations in class to kind of make this hopefully a little bit clearer. But as the light tries to go through, say, like a rope tries to go through a picket fence, or anything tries to, vibrate through a picket fence, or something that's got vertical slats, it can get through vertically. So we would say that's vertically, like this diagram here, would be vertically polarized rope, but vertically polarized light. That's what this is supposed to be showing you here. Filters at the microscopic level have molecules that only let the vertical vibrating electric field through for that particular filter. So we say now it's been filtered and it's polarized vertically. What we're going to be doing in class is taking two filters in a row, like we have over here with this picket fence idea. And once you get at the microscopic level, you're going to have filters that you cannot see inside them. What's going to happen, though, is the light is going to travel through the first filter vertically, let's say. But then if we put the second filter perpendicular to the first one, because with a horizontal filter, only horizontal vibrations can get through. But if you have a vertical vibration trying to get through a horizontal fence, it can't get through because it's trying to vibrate up and down, and that's its only vibration. It can't get through because only horizontal vibrations can get through. So nothing can get through that one if you have two in a row. If you have just the horizontal one by itself, horizontal light would get through if the original light was unpolarized. And then the sunglasses here at the bottom, let me go to the next screen. So these polarized filters have a special molecular structure. They're not just a dark piece of plastic. Now you can have just dark pieces of plastic, which tend to be cheaper than polarized sunglasses, but that's just a shade then. It's not a polarized filter. I'll talk more about that in class with some demonstrations. You can also get polarization by reflecting light off of a flat surface, any flat surface like a ground or a road or a wall. The direction of the polarization is the same as that of the surface. Let me just talk about the sunglasses here for a second. So when you pay the extra price for polarized sunglasses, they're not just shades. They have a special molecular structure inside such that it only allows vertically vibrating electric fields through those filters. Turns out that when light reflects off of roads or lakes, outside there's a lot of horizontal surfaces, not very many vertical surfaces. The light that reflects off those surfaces has a slight horizontal polarization. Reflected light is going to be more horizontal in orientation. It's kind of like skipping rocks. It comes off horizontally. Not many reflections have a strong vertical part. Direct light from the sun is just random. It's going to have vertical and horizontal components. So here in this diagram with the sunglasses, the red part of this shows basically the type of light predominantly that would be reflected vibrations, and those are going to be absorbed by the filters because the molecular structure does not let that light get through, that vibration, like the picket fence. It's going to absorb that light and turn it into heat. But the vertical vibrations do get through. That's just demonstrating this with these glasses. I'll show you some demonstrations in class. So polarized light is light that's vibrating in one direction.